This is lecture number 11. At this point, you know a great deal about the Skew T log P diagram, so now we're going to apply what you know and take a look at severe weather soundings and different types of severe weather, and also studying different types of winter precipitation and how you can use a Skew T and thickness values to determine what type of precipitation is going to occur, the form of that precipitation. We're going to start off with severe weather, and then in the second half of the presentation we'll study winter precipitation. Starting off with an important tool to use when forecasting severe weather and winter weather is forecast soundings. This uses model data to construct a sounding profile, and there's several advantages to this. The forecast soundings avoid having to only analyze the 0Z or 12Z sounding data. A lot can change in the atmosphere between that 12-hour period there. So as a forecaster, it's an advantage to see how is the temperature and moisture structure and wind profile of the atmosphere changing on an hour-by-hour basis. Forecast soundings avoid having sounding data only from the Raywinson launching points. When using the models, many different locations can be used, not just where they launch the weather balloons from. There's several models that are used to construct forecast soundings. There are websites available that in real time you can access the forecast sounding from various models, including the NAM ADA model, the nested grid model, the global forecast system, or the rapid update cycle. And when looking at the forecast soundings, here's some important information to look for. It's important to assess the instability. How stable or unstable is that sounding, and how does that compare using the different model soundings? Also get an assessment of the cap, different index values to assess the threat for severe weather, the depth and location of moisture. Moisture is a critical ingredient for both winter weather and severe weather. In severe weather, it's usually important to have fairly high dew points, a lot of moisture in the lower troposphere, where in a winter weather situation, it's important to have saturated air. It doesn't necessarily have to have a lot of moisture, since the dew points are going to be fairly cold in cold air. But the air doesn't need to be saturated and lifted to generate winter precipitation. The temperature profile is very critical, and for a severe thunderstorm situation, it helps to have significant cooling with height. In winter weather precipitation, that can be used to tell the difference between snow, sleet, or freezing rain, or just a cold rain. And then the wind profile is also important, and I'm going to next on the PowerPoint show different forecast soundings from various models for the same time period. Each one of these is going to be for 18Z on Friday, and we're going to compare these different models and see how much variation there are in the soundings from these 4 different soundings that we're going to look at out of central Oklahoma in around noontime. This first sounding is the rapid update cycle, and I'll point out some important features on here that you will not be able to read, but I'll include a packet where you can look at these soundings in front of you while I go over them. The CAPE value, the instability, is almost 1,500 joules per kilogram. The cap value is 4.0. So that's a fairly significant cap and a fairly significant amount of CAPE. So if there's enough of a lifting mechanism, it could break through that cap. It's also important to look at the moisture profile. This is a potential severe weather situation, so we want to look in the lower troposphere and look at the moisture profile. It's important to have high dew points in the lower troposphere. At the surface, that's a 20 degrees Celsius dew point. So that's almost 70 degree Fahrenheit dew point. So there is a rich amount of moisture in the lower troposphere. And interestingly, for a severe weather situation, it helps the thunderstorms to be even more severe if the air is actually dry here in the middle levels of the sounding. So abundant moisture near the surface with dry air above that, combined with warm air at the surface and much cooler air aloft, that combination together can produce significant severe weather. And we'll look at the next sounding, which is the Eta, and it also has about the same amount of instability and a little bit weaker of a cap, 3.1. So it looks fairly similar to the previous sounding, very unstable, a lot of moisture in the lower troposphere. Next, the GFS. It has a significant Cape value also of over 1,200 joules per kilogram, and the cap is 2.7, so this one has a little bit weaker of a cap, but it still has the abundant moisture and warm air in the lower troposphere and cooler air and drier air aloft. And then the last one is the NGM, and this is the sounding that looks significantly different from the others. On this one, the Cape value is only 20 joules per kilogram, and the cap is 2.4, so the instability profile looks very much different in the sounding. And one thing as a forecaster, you ask yourself, why is this sounding so much different from the others? In examining the sounding, you'll notice that the temperatures aloft here in the middle troposphere are warmer according to this model. And if you have warmer air aloft, that is going to decrease your instability. So we have three models suggesting that there's a significant amount of instability, and then one model that suggests there would not be much. So you as a forecaster has to determine, should you go with the majority of the models that suggest an unstable environment, or should you go with the minority, the one sounding that doesn't? So you'd want to look at additional weather data, look at surface and upper air charts along with the sounding, and ask yourself, is it more realistic for this to be an unstable situation or a more stable situation according to the NGM? And this is the 18Z radar. The sounding site is in here, and the models, most of them were suggesting that we'd have an unstable atmosphere here. There would be capping inversion, but capping inversion is at a level where if some lifting mechanism does come in, it should be able to break through that and generate storms. Off to the west, there's already storms that have developed in the Texas Panhandle and in northwestern Oklahoma. So either the cap is weaker in this region or there's more lifting that's occurring. If more lifting is occurring, then that can break through a stronger cap. And out here in central Oklahoma, either the lifting mechanism is not as intense or the capping inversion is stronger, or a combination of both. But as this day progresses, these storms are moving towards the east, and thunderstorms can develop outflow boundaries that come out of them. There could be a lifting mechanism out here that's associated with this that's moving towards the east. And so after looking at all the various data, looking at surface data, upper air data, you'd be more likely to come to the conclusion that this is going to be an unstable environment in the afternoon. You have daytime heating adding to that also with the abundant low-level moisture, so it's fairly likely there would be a thunderstorm outbreak with potentially severe weather also. These are the surface observations from 18Z showing how much moisture and heat energy is in central Oklahoma. This observation here, we got 82 degrees and it's only going to get warmer during the day likely. There's warmer air towards the south and the winds are coming out of the south at a fairly good clip, so you got some warm air advection, and if the sun comes out then you have solar radiation, so you definitely got plenty of heat at the surface and you have very moist air, high dew points. There's 69 dew point, almost 70-degree dew point. There are, however, some limitations to the forecast soundings. One of these is that it smooths the data out, so it's going to be less accurate and sometimes much less accurate than an actual sounding. But remember, those actual soundings had many limitations in that they were only launched at 0Z and 12Z, and they're only launched at specific locations. Forecast soundings have problems accurately profiling a capping inversion, and they'll also have the same biases that a model has. So if a model tends to be too warm or too cold, the sounding that it produces will also be too warm or too cold. There are special soundings that are launched, especially if it's in a potentially severe weather situation. It's important to get more data, because if there's more data, that information can be fed into the forecast models and it will make them more accurate. And plus, you'll have a higher saturation of data, so you as a forecaster have more raw data to go by when analyzing and diagnosing the severe weather situation. So a special sounding is a sounding launched at a time other than 0Z or 12Z to get an updated actual profile of the troposphere. And they'll usually launch that right in between the 0Z and 12Z time frame. When there's a potential severe weather event, there's several different sources that are important to check. Those are National Weather Service forecast discussions, Storm Prediction Center convective outlook and discussions. There's several different websites, and then also analyzing and diagnosing the weather situation with the forecast models, analysis charts, the current weather conditions, the Skew T's, and the satellite and radar data. Here are some dangers from convective storms that you're well aware of: lightning, flooding, convective wind gusts, hail, and tornadoes. And we're going to go over soundings and what you look for in a sounding to get an idea if one of these is possible or likely. Starting with lightning. Along with flooding is a top killer from storms. Lightning often does not get as much attention as other weather killers since victims tend to be isolated in numbers and spread through time over a large geographical area. A storm with abundant lightning will often display a significant value of CAPE along with a significant amount of moisture on the Skew T log P sounding. So if you have large CAPE, you're going to have a strong updraft. So the bottom part of your thunderstorm is going to be very warm. The top part of the thunderstorm is going to glaciate and get very, very cold. So you have a huge gradient in temperature within the thunderstorm. You have ice at the top of the storm and unfrozen moisture at the bottom of the storm. And in that situation, when you have a lot of moisture, it tends to generate an abundant amount of lightning. flooding, this is the greatest killer worldwide. And there's several different types of flooding events that can occur. Flash floods, such as from a thunderstorm that is slow moving, or a combination of slow moving and producing very heavy rain. River floods, when you have persistent rain over a period of time, and then the river can no longer handle that water, and then it floods over its banks, and that can produce a significant amount of damage. Inland tropical system floods can also produce a significant amount of damage. They can produce river floods. They can produce a very significant problem because the rain is very heavy, and this is especially a problem if the tropical system is fairly slow moving. And then a coastal flood also threatens life, such as the storm surge coming out of a hurricane. Flash floods, heavy rain from often slow-moving storms, especially if location does not have the capacity to handle much rainfall. So a location that doesn't have a lot of vegetation and usually doesn't have a lot of rain, when a location like that gets very heavy rain, flooding and flash flooding is very likely. If a location has a lot of moisture and the soil can absorb a lot of moisture as it falls, then flooding is not going to be as much of a problem. It'll take a heavier rain event in a more moist climate in order to produce a flash flood. A precipitable water value well above the climatological normal is an indication storms may produce flash floods. So if a certain location at a certain time of the year tends to have 1 inch of precipitable water, usually the vegetation is going to be adapted and the environment is going to be adapted to that much moisture in the air. But suppose that there's twice as much moisture in the air as normal. Suppose there's 2 inches of precipitable water over a location that usually only has 1 inch, and heavy thunderstorms develop in that region. In that situation, flash flooding is likely. Organized tropical convection. Tropical systems can dump over a foot of rain. A tropical system is a warm core saturated system. It has extreme values of precipitable water. The 500 millibar temperatures are very warm. In some situations, they may be above freezing. And flooding can be a serious problem, especially if they're slow moving. And there is a sounding there from Miami from when a hurricane, this was a 0Z sounding, and this was pretty close to the time that a hurricane was making landfall in the Miami, Florida area. And we'll go to the overhead camera, and I'll point out some specific details from the sounding, and it'll give you a good idea of the tropical environment that we're dealing with. I mentioned that we have extreme values of precipitable water. The precipitable water value is there. You'll have these notes in front of you, and you'll see that that's 2.9 inches of precipitable water. Anytime the precipitable water is getting near 3 inches, that is an extreme amount of moisture. Between 2 and 3 inches of precipitable water is extremely high. If a thunderstorm occurs in that situation, it's generally going to have very heavy rain. And with the tropical system, it's dumping that heavy rain for an extended period of time, so it's not just one thunderstorm that's producing that rain. It rains continuously for hours and hours, so that's why you can produce a large amount of rainfall, over a foot in many cases. Also mentioned that it has a warm core structure. So the temperatures are, for any sounding, the temperatures are well above what they would normally be, especially as you go higher aloft. You'll notice on the sounding that this sounding is well to the right of the page. It starts off with fairly warm temperatures at the surface, and the freezing level you do not encounter until you almost get up to the 500 millibar level. So our freezing level is given on the sounding as 520 millibars. So that's very high. You have to go all the way from the surface all the way up almost to the 500 millibar level to get to a temperature below freezing. And then another thing to point out is that the temperature is about equal to the dew point all the way with height on the sounding. So that's why you have an extreme amount of moisture, because the warm air is going to have the capacity to have more moisture, and if it's saturated, it has the maximum amount of moisture that it can have in the air for that temperature. So you have a sounding of high dew points and warm temperatures all throughout. So that gives you a good example of the warm core structure that is in a hurricane. And here is a radar of that hurricane that was moving through Miami. It was a minimal hurricane, a Category 1 hurricane that moved through Miami and did some significant damage, several $100 million worth of damage from the system from flooding and the high winds. This is Hurricane Katrina, and this was the same hurricane that several days later did catastrophic damage on the Gulf of Mexico coast in southeastern Louisiana, Mississippi, and Alabama. In our next lecture, in lecture number 12, we'll go over that some more. Convective wind gusts are a threat from severe thunderstorms. Those are caused by strong downdrafts. A downdraft is caused by evaporational cooling aloft of the air. The cooler air falling through warmer air and precipitation dragging the air downwards all contribute to a significant downdraft. And how do you analyze this on the Skew T-log P? You look in the middle troposphere, and if you have a significant dew point depression, if your spread between your temperature and dew point is large, that's an indication there's dry air in the middle troposphere. And if a thunderstorm develops in that environment, you're going to have entrainment of that drier air into the downdraft, and that's going to promote evaporational cooling. And so you have the air aloft being evaporationally cooled. That's going to make it more dense and cause it to accelerate towards the surface. You can get microbursts and macrobursts in that type of situation also. Hail is influenced by the freezing level, the updraft strength, the elevation, and wind shear. So if there's a severe thunderstorm that's developed, if the freezing level is closer to the surface or the elevation is higher up, then there's more likely to have large hail, since there's a larger hail growth region in the thunderstorm and there's not as much time for the hail to melt as it's falling toward the surface. The amount of CAPE is very important too. A large amount of CAPE can compensate for all the other factors. A very large CAPE can produce large hailstones in a severe thunderstorm. The wind shear is important too. The more wind shear, that helps make the storm more severe, and it can cause it to generate larger hail. Hail is most common in the higher elevation regions where the CAPE can be high. So it's a location where it has a lot of instability and the elevation is high. A location in the United States where you find this combination of where you have instability and high elevation is in the high plains and adjacent regions to that in the middle part of the United States. So like Wyoming, Colorado, Kansas, Nebraska, that region in there, where you have that combination that region of the country tends to have the largest hail. So as I mentioned, the most important factor in hail size is going to be CAPE, the amount of instability. Hail deaths are rare, but the damage caused by hail can be extensive. It can do a lot of damage to crops. It can do a lot of damage to automobiles. The tornado can be a big news event since damage can be very destructive and many lives can be lost in one event. Supercells and other strong storms can produce tornadoes. As we've gone over in the previous lecture, it's the helicity and CAPE in the lower troposphere in the 0 to 3 kilometer layer that are important to analyze on the Skew log P diagram, since those are important contributors to the tornadic environment, especially significant tornadoes. And now we're going to look at some example Skew-Ts, and on each one of these we're going to assess whether there's a high lightning frequency, whether it could cause flash flooding, convective wind gusts, large hail, or a tornado. And with flash flooding, there's several other factors to look at too, such as the soils being saturated already so that you'll have a more immediate runoff. If you have an immediate runoff combined with heavy rain coming down, then you're more likely to have a flash flooding. And with the lightning, remember we mentioned to look for CAPE, high CAPE values, and high precipitable water. For convective wind gusts, we're going to look for dry air in the middle part of the troposphere. For hail, we want to look for the amount of CAPE. And then there's also some other factors that are important, such as the elevation and the wind shear and the freezing level. And then the tornado sounding, where significant tornadoes tend to have strong directional and speed wind shear in the lower troposphere that generates high values of helicity, and then it also has significant CAPE, a significant tornado event, a large tornado. There tends to be a significant amount of CAPE in that environment, and the lower that CAPE is to the surface, as we've gone over the previous lecture, then that can make the tornado event more significant. So let's look at our first sounding here. And this is a sounding that shows an example of where strong convective wind gusts can occur. So in the middle troposphere, we have a big spread between our temperature, which is in red here, and our dew point, which is in this green color here. So you have a large dew point depression in there. So you got a lot of dry air aloft. Here's our parcel here, so you have a significant amount of CAPE, the parcel warmer than the environment. You got high dew points, although it's dry here. Once you get down closer to the surface, you have a rich amount of moisture and thermal energy. So a thunderstorm developing in this environment would be a good candidate to produce strong convective wind gusts. It could also produce large hail. You have CAPE of about over 2,500 joules per kilogram, very unstable atmosphere. And then you have a little bit of helicity. This could be better. The wind speed and direction change could be better, but often in the mesoscale environment, the helicity may be more impressive than you see on the sounding. Remember, this is one sounding, this is just one location, one snapshot in time. A lot can change with this wind environment on the mesoscale, time and space scale. Here's another sounding which also could produce the same type of severe weather that we looked at in the previous sounding. It has a significant amount of CAPE here. It has this dry air in the middle troposphere, and you're generating this large amount of CAPE because you have warm air and moist air in the lower troposphere you have a steep lapse rate of cooling in the middle troposphere, and if a lifting mechanism comes through here, you have a potential instability too, where the rising parcels of air, they're going to cool off more here than they are down there, so that's even going to increase your lapse rate further. So this is an example of an extreme type situation, where this situation is over 4,000 joules per kilogram CAPE. And it had a helicity value of 220, which, as I mentioned again, the mesoscale environment, once the storms develop, is often going to be even greater. You got strong wind speeds aloft too, so you have storms that develop in this environment would be very severe. And one more, the flooding sounding that we've already looked at in Miami. If we have a high value of precipitable water, a slow-moving tropical system, or the same thing applies to slow-moving thunderstorms. It can produce a lot of rain and cause that flooding. As I mentioned, especially if it's in a drier type environment. If you took the same sounding and moved this over to a dry climate, because Florida's a pretty humid climate, they had flooding there, even though they do have a lot of vegetation and the soil can absorb a lot of moisture. If you have a precipitable water value that's high and you have slow-moving thunderstorms over a dry area, then you immediately get some flash flooding that'll occur. Next, for the second half of our lecture, we're going to look at winter weather, starting with winter weather problems. These include transportation problems, power loss, damage from weight of ice, economic slowdown. And a lot of these slides I'm going to show here, you know this information already, but it's information that's important to tell the public. It's important to give them this advice that I'm going to go through over and over again, and it's advice that undoubtedly you've heard before. Slick roads, longer travel times, traffic collisions, reduced visibility, aircraft icing, these are all problems in a winter weather situation. Traffic collisions. Vehicles that do not travel slow have a much greater risk of collision on icy roads. A lot of drivers, they don't change their driving habit when there's an icy road, and that can create a dangerous situation. Especially if they're driving and they think the road's not icy, then suddenly they go on a bridge or overpass that it is icy. If they have a high rate of speed, they'll often lose control of the vehicle. Traction is less on icy roads, therefore keep a safe distance from the cars around your other car. That's good advice to give the public. Be especially cautious on the bridges and overpasses since they freeze first, since they're most exposed to the air. When the air drops below freezing, it's the bridges and overpasses that drop below freezing first. And then this is advice I like to follow the most, just stay off the roads, just stay home, and it's much safer just to stay at home. Reduced visibility can make traveling conditions more dangerous. Wind-blown snow reduces visibility even further. Traffic signs can be difficult to see. And then make sure that you remove all the ice from the windows before you start driving. Some mornings you may have a lot of frost on the windows. If you don't get all that off of there, that could significantly reduce your visibility and being able to see other drivers around you. Power loss. This is especially dangerous for the elderly or people that are not able to react quickly to changing weather conditions or drastically changing environment. Of course, power loss can produce significant problems very quickly if you're not able to heat the home anymore. Power loss increases risk of dangers from cold temperatures. It reduces the ability to get information. So it's important to have battery-operated devices, such as battery-operated radio and TV so that you can continue to get information even when the power goes out. So have the backup power supply, the batteries for the flashlights and the radios, and be able to keep warm without electricity. So this is all stuff that most of this needs to be done in advance, even before the winter comes. People should have all this stuff prepared so they're not out all panicking trying to buy all these things when a winter weather event is coming together. Damage from the weight of ice. This is especially a significant problem with freezing rain. Power lines and tree branches torn down. Deep snowpack on building that can cause a roof to collapse and damage to the roof. Once it melts, that can often lead to a leaking roof. And falling ice from structure can damage vehicles, so you don't want to park your car near where ice could fall off of it. And it's also important to keep a safe distance from other vehicles because ice could fly up in the air off of another vehicle and hit your windshield, and that would be a very bad day. It can also cause a temporary economic slowdown. It's a reduction of sales in general, less traveling, and loss of school and work days. But we want to concentrate on this lecture for the winter weather part on how we forecast different types of winter weather using the Skew. Forecast soundings are a commonly used method for forecasting winter precipitation type. The temperature profile of the troposphere helps determine the precipitation type that will reach the surface, temperature of the precipitation growth region, and we'll go over what the growth region is. It's also important. The snow growth region. In winter, precipitation, especially moderate to heavy precipitation, usually develops as snow aloft, regardless of the form of the precipitation that reaches the surface. Lifting of saturated air in air with a temperature of less than minus 10 degrees Celsius is the snow growth region. Temperatures that are warmer than this, the temperature could still be below freezing. Let's say the temperature is between 0 and minus 10. At those temperatures, it's more likely to promote liquid, supercooled water droplet growth instead of ice crystal and snow. And we'll go through different types of winter precipitation, and we're going to start off with snow. Clouds need to be cold enough to support the ice crystal growth. So you need to have minus 10 degrees Celsius or colder temperatures and lifting within that layer of saturated air. If the clouds are only composed of supercooled water, then the snow will not occur. And for snow to reach the surface, there needs to be a temperature profile cold enough to allow that snow to fall all the way to the surface without melting or being modified and changed into sleet. So on the overhead, we'll review the main points that you'll want to know here when forecasting snow. The thickness value and snow, these thickness values are real important looking at the soundings. And there's different software that you can use that you can put the sounding information on there and determine these thickness values for different layers. So for snow, generally between the 700 millibar level and the 300 millibar level in any type of winter precipitation event, the temperatures here are generally below freezing. So we really don't worry about this layer here when it comes to temperatures, when we're trying to forecast the precipitation type, because this is always below freezing. It's this layer in here That's the most critical to look at between 1,000 millibars and 700 millibars. The temperature structure in this layer here is what is used to determine whether it's going to be snow, sleet, or freezing rain, or just rain. If this thickness, which thickness is the distance between two pressure levels, and you'll remember that's a function of the temperature. The colder the temperature is, the lower the thickness value is. If the temperatures warm up, then the thickness value is also going to increase. So for snow, you want to look at the forecast soundings, and it helps look at as many models as you can, since one particular model may have a cold or warm bias. And look at this 1,000 to 700 millibar thickness. If that is less than 2,820 meters, and you also have precipitation that's growing in the snow growth region, then snow will occur in that situation. So this thickness less than 2,820, if it's less than that, then it's very likely that this whole layer is below freezing. Since this is always below freezing up here, once this goes below freezing down here, then you have an entire profile that's below freezing, and if you have ice crystal growth in the snow growth region, then that snow will fall all the way to the surface. So in our notes, if the precipitation develops in the snow growth region, 1,000 to 700 millibar thickness is 2,820 meters or less, and precipitation reaching the surface will very likely be snow. Now we'll move on to another precipitation type known as sleet or ice pellets. And we'll go over how those develop. And here's how a sleet or an ice pellet develops. The snow partially melts aloft and then refreezes into balls of ice. The melting is partial, and it's very important that the melting is only partial, not complete melting, but a partial melting of that snowflake, so that there is still an ice nucleus for water to freeze upon once temperatures drop below freezing again while the precipitation is falling. Now, if the snow is completely melted as it's falling aloft, and then it falls through a sub-freezing layer, then instead of turning into sleet, it'll turn into supercooled liquid water drop in that situation. So that's why it's so important to determine if it's going to be a partial melting or a complete melting. If it's a complete melting, then it's either going to be rain or freezing rain. If there's a partial melting and it falls through a sub-freezing layer below that, then that's a situation where sleet and ice pellets can occur. Here are the requirements for sleet. First, you have to have snow forming aloft in the snow growth region. And the capital EWL, we'll go over exactly what that is here. The elevated warm layer, that's what that stands for. The elevated warm layer for sleet, it needs to be less than 4 degrees Celsius. If the temperature within a layer of air aloft is warmer than 4 degrees Celsius and snow falls through that, it's going to completely melt that precipitation. Then sleet could not occur. Also, if the elevated warm layer is less than 400 meters thick, then usually just partial melting will occur and not complete melting. But if that thickness is greater than 400 meters, especially significantly greater, let's say it's like 800 meter, then that snow is going to completely melt. And so then sleet would not occur in that situation. And then for sleet, you also need to have that sub-freezing layer below the elevated warm layer. So 1,000 to 850 millibar thickness, less than 1,295 meters. And we'll go to the overhead and look at the graphic of an elevated warm layer, and then look at how and review how ice pellets develop. So the elevated warm layer. Here's the surface. You have a layer of air aloft that is above freezing. Above that layer, it's below freezing. You've got sub-freezing temperatures up here. And between the surface and the bottom of the elevated warm layer, you also have sub-freezing temperatures. So it's the depth and how warm this elevated warm layer is will determine whether sleet will occur or if it will be freezing rain. If it completely melts it and it falls to the surface and the surface is below freezing, then it'll be freezing rain. If this elevated warm layer is generally less than 400 meters thick and the maximum temperature is not greater than 4°C, then you'll get partial melting. And the partially melted snowflake will then, it'll look like rain, but there'll still be an ice nucleus in there. When it falls through the sub-freezing layer, then this ice nucleus will refreeze the water droplet all the way again, and sleet will reach the surface. So we'll review how the ice pellet develops and reaches the surface. So we have the snow growth region aloft and winter precipitation. All the precipitation that initially forms high aloft is snow. So you develop that snow, so you have lifting of saturated air here that's developing snow. You have falling snow. And then it falls to this elevated warm layer if there is one in it. So if there is an elevated warm layer, for a ice pellet or sleet situation, you have to have an elevated warm layer because you're going to have the partial melting occurring. But that elevated warm layer needs to have a temperature that it does not go above 4 degrees Celsius, or that'll melt all the precipitation. And it's got to be less than 400 meters thick. And these are just guides. I mean, these are not absolutes here, because it's going to depend on other factors too, how large the precipitation particles are and how heavy the precipitation